Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're getting way out into the cosmos. We defined the nature of redshift last time, and so redshift allows us to get distances to galaxies, and with those distances to galaxies we can figure out how things are arranged in space. And that's the structure of what we're talking about this time is groups and clusters of galaxies, because once we know where they are in the sky, we can see that they're actually grouped. All right, so the first most obvious group that we know about is called the local group. And the local group is about 54 or so galaxies comprised the Milky Way and Andromeda. It's our little local neighborhood in the universe. Now the Milky Way and Andromeda are of course falling towards each other, so they're all bound by gravity. And the diameter of the local group is about 3 or 4 megaparsecs, and it contains about 5 or so bright galaxies, and with 3 spirals, and one some big elliptical orbiting M31, which is M32. There are a few dwarf ellipticals, and lots of little dwarf spheroidals, dwarf irregulars, and all sorts of little bitty things. Now the total mass of the local group is about 5 trillion solar masses. That's about 5 times 10 to the 12th solar masses, because each of the Milky Way and Andromeda is a few hundred billion stars, with a lot of dark matter in between. And so when you add up all the stuff and all the dark matter, you got a lot of mass there. All right, so the local group is our little neighborhood. And there's what it kind of looks like. There's a lot of space between galaxies because remember, galaxies are where the stars are. But we also know that in between the Milky Way and Andromeda, there's an enormous amount of dark matter. So if we could possibly see all the dark matter, it would fill this space. It would be like this big glow around the Milky Way and around Andromeda. And in fact, it would probably be about 5 to 10 times the size of it. So this whole bucket would be filled almost to the brim, almost completely smoothly with dark matter, if we could see it. So the local group has a certain kind of orientation. So let's take a little tour. There's what the Milky Way is. We always center ourselves in the Milky Way. Lots of little dwarf galaxies, large and small Magellanic Cloud around us. And if we go up to the M31, we see it's over here. The Triangular Galaxy M33, M110, and M32 are also there, some elliptical galaxies. And we can see their arrangement in space. And here's a beautiful image of the Andromeda Galaxy taken that was shown in an astronomy picture of the day. Another wonderful astronomy picture of the day picture comes here of the Triangular Galaxy, and the large and small Magellanic Clouds are part of the Milky Way of the local group as well. So the Milky Way is the local group is kind of a thing called a group, and so there's different kinds of ways that galaxies come. They come in groups and clusters. Groups have about 3 to 30 or a few bright galaxies, and clusters have at least 30 to a couple hundred bright galaxies. And groups and clusters typically range from about a megaparsec across to about 10 or 15 megaparsecs across. That's millions of parsecs, which means about 30 million light years to about 50 million light years. And they're filled with many, many, many more dwarf galaxies than bright galaxies by their counts. Now there's groups and clusters of galaxies. They range in mass between 1 trillion and 1,000 trillion solar masses. So there's a lot of mass that tends to be in groups. And thousands upon thousands of galaxy clusters have been known and cataloged. So here's some dwarf galaxies in the Perseus cluster. Here's one of them is called a Hickson compact group. So you see 3 spirals, 2 interacting, and one elliptical, and possibly a very, very distant spiral in the lower left. Here's Hickson compact group 31, and that's another group of galaxies. Here's its appearance. So you can see this is not very big. So the Hickson compact groups are kind of an exception to this, where they're very small volumes of space with smaller galaxies that are interacting as groups. Here is Seyfert Sextet, which is another small group of galaxies all interacting. And the Hickson compact groups themselves were studied by Hickson, and he created a series of groups that were between 50,000 and 200,000 light years in diameter, and always contained maybe 1 or 2 spirals and a few ellipticals, but they tend to be centered on spirals. And we can see a couple of groups in here with the lower left, which is the Stephan's quintet, of which only the 4 on the lower left is Stephan's quintet, and the upper right we just have an apparent group The big one in the foreground is actually a foreground galaxy, but the ones that are above it and beyond, that's actually a group. So groups get to larger groups that we call clusters, and clusters of galaxies are much larger and can contain thousands of galaxies. The Virgo cluster is the nearest large galaxy cluster to the local group. It's a relatively loose cluster, meaning it's not really tightened in and everything together, but there are two bright ellipticals, M87 and M84, that comprise it, and it lives at a distance of about 18 megaparsecs. That's about 60 million light years, and that spans about 2 or 3 megaparsecs in diameter. Composed of about 3,000 or 4,000 galaxies, and most of them are dwarfs, of course. And the total mass is really huge, 100 trillion suns. But the Virgo cluster has a large composition. As you can see, the spread out nature of all the fuzzy objects, that's what we mean by not compact and loose. And so there are much tighter clusters of galaxies, which we'll see shortly. And here's some of the outskirts of the Virgo cluster. We kind of rotate it around, and here's the core of it, highlighting M84 and M86, which are two giant elliptical galaxies. You can see that there's some spirals inside, but lots and lots and lots of objects that are identified as galaxies inside here. Here's an extended mosaic of the Virgo cluster, and here's wonderful thing from Astronomy Picture of the Day to go hunt around yourself. Here it is again. So we can then go jump and look at rich galaxy clusters, and rich galaxy clusters contain thousands of galaxies. And they can span up to about 10 or so megaparsecs, and they have about 1,000 trillion solar masses. So remember that the Milky Way is about 100 billion solar masses, which is about 10 to the 11th. So this would be a 10,000 Milky Ways in terms of mass. They always at least have one giant elliptical deep in the center, and rich galaxy clusters have many ellipticals swarming around the center, and the gravitational pull from them usually makes these galaxies spin up to 1,000 kilometers per second as they whip around inside of them. Now that 1,000 kilometers per second inside galaxy clusters has a lot of implications. And here was the Coma Cluster, which is a more compactified galaxy cluster, and there it is, the center of the Coma, which is, you can see lots of elliptical galaxies in here and a couple giant ellipticals, but we don't see a lot of spiral galaxies inside a dense cluster like Coma. And we can see two kind of groups over here. There's two centralized groups of galaxies with all the fuzzy patches are distant galaxies. And another rich, dense cluster, Abell 02345, where a couple of giant ellipticals surrounded by a swarm of elliptical galaxies. And here's Abell 02439, which is a long sort of string of galaxies. And another one, 2350, which is kind of an extremely distant galaxy cluster that seems to have a number of ellipticals in it. And Abell 2351, which kind of looks like a star field, but actually is a group of fuzzy little galaxies far in the distance. Just to give you an idea of what galaxy clusters look like in the Digital Sky Survey, that's what this is all doing, is that we can see that these little tiny fuzzy things that are deep in the distance that were seen photographically originally, and so counts were done. And here's Abell 2353, another one that's a nearby galaxy cluster. And the Hercules cluster is a more loose one, and it is spread out further and has more spirals in it. Abell 98 is a much more rich cluster with a dense group of ellipticals around a giant elliptical at the center. And again, Abell 98, I believe that was the same thing, Abell 98, different orientation. Now, the fun thing about galaxy clusters is they're held together by gravity. Now, gravity's keeping them together, even though the relative speeds of them are whizzing around at 1,000 kilometers per second. Now, when you have something that's 100 billion solar masses and another thing that's 100 billion solar masses, or thereabouts, and they're going 1,000 kilometers per second, that's too fast for them to stay together. And since that's too fast for them to stay together, their average motions, as we learned with the nature of dark matter when we talked about that when we looked at the Milky Way, there has to be something there that keeps them together. So the total amount of mass that must be there such that these clusters actually exist, given the fact that they are composed of these large galaxies, the mass must be enormous. So people looked for the amount of mass that was there, and they hunted in all sorts of wavelength bands, from radio to infrared to optical to X-ray. And when X-ray views were taken, it was found that a huge amount of X-ray gas existed. But it wasn't enough in order to make up the mass that held the entire cluster together. But most of the matter in all galaxy clusters is in the form of dark matter and can make up to 90% of the mass. And that's what keeps them together from flying apart, even though they're moving very fast. In X-rays, we see that of the remaining normal matter of the entire galaxy cluster, which is 10% of like normal matter. We assume dark matter is not normal matter, but the remaining normal matter, most of it's an extraordinarily hot 10 million to 100 million Kelvin gas, which can only be seen in X-ray wavelengths, and it's typically superheated material that is emitting light through what's called thermal Bremsstrahlung, and that Bremsstrahlung action means that there is as one atom moves at nearly the speed of light, relativistic thermal Bremsstrahlung, or even just Bremsstrahlung itself. If they're moving extraordinarily fast, then as they pass by each other, their directions change and they lose energy. But they don't lose a huge amount of energy, but it's just enough in order, and when they turn around and get pulled by an atom pulls on an ion or pushes on an ion, that Bremsstrahlung, or braking energy, makes X-ray light. And so that can be done in the presence of a magnetic field or just simply in the presence of other charged particles. And when it does that, well, if it's in the magnetic field, it would be called synchrotron, it would be rotating, it would get radio light. But thermal Bremsstrahlung is a hot gas where the way it's emitting light, because it's not dense, it is not a dense hot gas, it is an extraordinarily diffuse hot gas with only 100 or 1,000 particles within a cubic meter. So they're incredibly, incredibly underdense areas. So the fact that it's glowing so intensely in X-rays means that there's a huge amount of it. So we see that in the optical image here from Abell 2199, we see a bunch of galaxies, but in the X-ray image, we only see the hot, hot, hot gas, which is centered on the X-ray, which is centered on the giant elliptical at the center. So this X-ray gas comprises most of the mass of the cluster that's normal matter, and that normal matter interacts with light. But even that is not enough to keep it together. So the studies for X-rays emitting gas in galaxies has been done for a very long time, and when Chandra X-ray Observatory went up, what was one of the major studies is to map out X-ray distributions in the sky, and here's some Chandra maps of X-ray emission in the sky of various galaxy clusters. And we can see that the X-ray emitting gas greatly extends and encompasses and envelops the normal luminous matter. The vast majority of all the gas of the matter, of the normal matter in a galaxy cluster, is about 90% of it is this hot X-ray emitting gas. So if 90% of a galaxy cluster is dark matter and 90% of the normal matter is this hot X-ray gas, then we're only seeing 1% of all the normal matter when we take a picture with a photograph in optical light, where we just see stars. So stars and gas and dust make up only 1% of all the mass of galaxy clusters. Most of the rest is in this hot X-ray emitting gas. All of the rest is in dark matter and this hot X-ray gas. So here's another image of the Chandra X Observatory looking at the hot X-ray emitting gas of a massive galaxy cluster, a rich, rich, rich galaxy cluster deep in the distance. And we can see that there's an enormous amount of X-ray emitting gas. This X-ray gas is probably being created by the formation of this galaxy cluster, as well as enormous star formation and possibly active galactic nuclei, which we will talk about in the future, where active galaxies spew out huge amounts of material into the intercluster medium, thus probably heating up this gas. And so the gas is at millions of degrees. So it's probably been that way for a very long time, but it needs to be reheating because as it emits light, it cools down. If it cools down, it's falling towards the center because gravity pulls things towards the center, as you can certainly see from this image. So something's got to reheat the gas in order for it to have this great extent, so it can stay at tens of millions or 100 million Kelvin. And that's probably due to active galactic nuclei as the galaxies then collide and the supermassive black holes in their centers merge and then form quasar-like activity, which we'll talk about soon. All right, so the largest known structures, largest known structures, are what are called superclusters. And superclusters are enormous clusters of galaxies, or just huge, vast, amorphous, lumpy groups. And they can range up to sizes to 150 million light years, or 50 million parsecs. And their masses range from 1,000 trillion masses to up to, quite a bit. 10,000 trillion masses, which is an enormous amount of mass. And they tend to be long filamentary structures and separated by enormous voids that span the sizes that are as big as they are. Now, superclusters are dominated by, inside of the clusters themselves, mostly empty space, because it is filled with dark matter and X-ray emitting gas, right? So, but it's amazing to look at such an image like this from Courtois Helene et al. In their Cosmography of the Local Universe. It was published in 2013 Astronomical Journal, and I get the link there for you from Archive if you want to go take a peek, because this is worth taking a peek at, is that you see that there's these enormous voids. And these huge voids make part of what we're looking at around here. And the local group is right down in the center there, just off to the side, to the left of what's indicated by Centaurus. So the local group is part of the local Virgo Supercluster. So what's that? The Virgo Supercluster is what is now on this image that you see here. This is a map of all the galaxies in the neighborhood. And so this was made, of course, with using positions in the sky and their redshifts, and then using the Hubble relation in order to map. Because you can't get Cepheid variables for all of these things, but you can very easily get redshifts. So redshifts are fast, Cepheid variables difficult. So now that we're talking about individual galaxies, if we know their distance, it's because we're correlating it using a well-calibrated Hubble diagram that relates the redshift to the distance. So now this is how we know their distribution in space away from us. So the Virgo cluster of galaxies is off to one side, and we've got these little minor clusters, the Virgo Libra, Centaurus, Hydra, and Ursa Major. This is called the Virgo Supercluster. It has an enormous amount of mass, and it's centered on roughly the Virgo cluster of galaxies. And as the local group falls towards the Virgo cluster, the others are kind of grouped together, and this is a roughly gravitationally bound object. Now but in 2014, Tully and a number of other astronomers redefined the nature of the local superclusters and redefined the Laniakea Supercluster. The Laniakea Supercluster, it spans many hundreds of about 100,000 galaxies, goes over 40 million light years, up to 500 million light years, almost a half a billion light years across, and has a mass of at least 10 to the 16th and the 15th of solar masses. I think I've made a typo there, so they have an enormous thing. There are 4 major subparts, and the subparts are the Centaurus cluster, the Virgo cluster, the Hydra cluster, and I think there's another one in there. I think of the Dorado group or Fornax group or the Pegasus cluster. Those were used to be separate superclusters, but in 2014, the astronomical community adopted Tully and team's definition of the nature of a supercluster, because now the ability to actually resolve the relative speeds of things could be deduced and removed from the cosmological measurements of the redshift. So now you could get a position in the sky and base the nature of superclusters off of how things apparently are moving in the sky. And so utilizing the apparent cosmic flow of galaxies, you can redefine clusters of galaxies. So the Laniakea Supercluster was defined in such a way, and it's known this is too big to actually be gravitationally bound and will probably be shredded by the expansion of the universe at some point within the next few billion years by the push of dark energy. So the Laniakea Supercluster is the redefinition of the local supercluster. So let's kind of zoom back into a closer thing. So let's look at what we mean by the Virgo Supercluster. This is again from Helena Courtois' paper, the Cosmography paper that we talked about later, and I'll give a reference for that soon. And we see that the Milky Way is off to kind of the outskirts of some side. There's the M81, M82 group over there to the right, and the Virgo Cluster is 60 million light years away, and the Ursa Major loose cluster off to the side. We see that M81 and M82, which we highlighted many times off to the side, is pretty close by. And the Centaurus A is a bright radio galaxy that's seen in the southern sky, and the Sombrero galaxy M101 is up there, is up in the sky, up over there too. So we notice from this image that there are lots of empty spaces. So the universe is kind of foamy on the largest size scales. The largest structures, such as the Laniakea Supercluster, are about 100 to 200 megaparsecs in extent. That's enormous, up to about 500 million light years across. And those structures are only kind of semi-temporary because they're not gravitationally bound, so on the largest size scales. But they still do have some sort of coherent appearance. And so the actual definition of where clusters begin, end, and superclusters begin is kind of up to taste and current researchers, whoever working on it, and then people just saying, well, that makes sense or not. So it's actually kind of an open-ended current area because Laniakea was only defined, of course, in 2014, so people are really working on it. So clusters and superclusters are arranged in these kind of filamentary or sheet-like structures and sheet-like structures, and their actual volume occupies only about 10% of the space. So the rest is huge voids, and they're big empty bubbles, and these bubbles of voids can be, up to 100 million light years, up to 150 million light years across, or 25 to 50 megaparsecs across, and they have vastly fewer numbers of galaxies than superclusters, up to 20 to 50 times fewer galaxies, and in fact, they might have none. So the exact number of galaxies inside of voids is not well known. So here is there's an important, credible one called the Great Wall, the Sloan Great Wall. And you can see they come in these kind of lumpy sorts of structures. And notice we're looking now at surveys. So a survey shows we're looking in velocity space. And so we can assign distance, which is distance in megaparsecs, but it's much easier just to call what the distance is. We know that the distance is related to the Hubble flow. So we don't really need the distance. We just say how fast it's rushing away. So we have a kind of a pizza pie diagram, and this I believe is a 2DF survey or a Sloan Digital Sky survey, and I forget which it is exactly, but we see that there's this would be Sloan because of the orange marks out the Sloan Great Wall, but we see that there's these lumpy structures and they're foamy. But if you look, that they're foamier, actually are lumpier as you get closer and closer to us, meaning velocity goes to zero. So the Milky Way and we are observing from the vertex of these pizza pie slices. And as we look out towards the edge of the pizza slice, we're looking farther and farther and farther away and further back, and they're much more distant galaxies. So we're at the center of the observation, looking either north or south. All right, so here's a better view of that. And once again, you can see that if you look at the distance of things that are approximately 700 megaparsecs or so, we see that things get more spread out, or velocities or up to 50,000 kilometers per second or so, and greater. We see that it's harder to find galaxies because they're fainter, and you have to have deeper surveys in order to find them. But we see that there's greater structure nearby, or stronger, more larger structures nearby. And that's a result of gravity. So the Sloan Digital Sky Survey endeavored and continues to endeavor to map the galaxies in the cosmos. And they've released many data sets over the decades that they've been working. In fact, I started my graduate career in the early 90s by beginning some of the very rudimentary networking to connect Apache Point Observatory down to New Mexico State in the lab area, so that we could see that. So it was an early use of early networking. So that was kind of a nice way to begin a career. Anyway, the Sloan Great Wall is an enormous, enormous discovery. It's about 450 million light years long, about 60 or 150, or about 60 megaparsecs high, and about 5 megaparsecs thick, and has a mass of over 20,000 trillion solar masses. That's enormous. So, I mean, it's almost getting silly to even talk these big numbers. But remember that 10 to the 16th means that's how many suns there are. So we really should start to have a new unit in terms of Milky Ways. And a Milky Way unit would be 100 billion solar mass. So if we just use 100 billion, which would be 10 to the 11th solar masses. So this would be 200,000 Milky Ways would be about the size of that structure and how many things are in there. So 200,000 Milky Ways comprise the mass of that thing. And there's not many things that are bigger in structure than about 300 megaparsecs. If you do Google around, you will find some odd things such as very large groups or large quasar groups that seem to be much larger than that. But they seem to be actually larger than this kind of structure. But notice that we don't really find structures larger in great numbers than 300 megaparsecs in size. And here's another view of the Sloan Great Wall. And there's another wall group that was seen by CFA, the Center for Astrophysics survey. And they were looking, all of them were looking in velocity space. Notice in these pizza diagrams, we always look out towards the edge. And these things are given in terms of right ascension, which is left and right in the sky across a pizza wedge. And we're at the vertex looking outwards. And here's another great galaxy survey called the 2DF survey. And so we see lots of filamentary structure, and wall-like structures and voids. And each of the points is now not a star, but a galaxy that is up to billions of light years away. And we can see the relationship between the distance in billions of light years and redshift. And redshift is up to about 0.2. Remember, redshift, we defined it in the previous lecture as being the change in wavelength compared to the rest wavelength. And it's about 20% is the redshift. So it's been changed by a factor of, the redshift has been altered by a significant fraction. Not doubled in terms of wavelength, but extended by 20%. Whatever it is. So if it's a wavelength of 1,000 nanometers, then it is now 1,200 nanometers long. So it's been extended by 20%. And that happens when something's about almost 2 billion light years away. So you really have to get very far out to get significant redshift. And there's another view of the 2DF survey. And it leads to a very incredible question. How did galaxies form? The existence of this large-scale structure, meaning all these voids and filaments and groups and clusters, galaxies have to form in these structures. So the structures themselves are created and shaped by gravity, and dominantly by dark matter, because we've learned that clusters themselves would fly apart if they weren't composed of dark matter. So they're moving really fast. They're composed of mostly dark matter. The structures are shaped by the gravity of the dark matter and the hot intercluster gas that permeates them. So there has to be huge amounts of concentrations of matter where the galaxies form. So we should expect that the dark matter web should look very similar to the web-like structure that we see here. And that will come up when we talk about large-scale structure formation as part of the Big Bang. So let's go back to Courtois and Helene et al., who are looking at the map of the local universe, and this just predates Tully's definition of Laniakea, and it looks at things in terms of the local speeds. And in fact, this set of data is what helped to define the nature of Laniakea. So we see that, let's start with the local group, and the local group in Milky Way and Andromeda and M101 and M81 group and all that stuff. Remember M81, M82, way over there? There's lots of little dwarf galaxies next to them. But you can also see that there's an enormous void off to above and below the plane of the Milky Way, which is really fascinating. And if we look down from that local void on top of it, we see that there's a group, a tiny little grouplet over by M81, which is its own group of galaxies, right? And we see M83 has its own group, and Centaurus A, which is a bright, bright, bright radio galaxy. When we talk about active galaxies, it'll be in there. And we see these things are composed of little groups. And if we then zoom out a bit bigger, we see again the location of the Virgo cluster of galaxies, which has a few thousand galaxies inside it. And we see all the little tiny mini groups that are close by. And then we can kind of look even a larger size scale and notice that the Coma Cluster is much more distant. And we get the beginnings of the Great Wall. And the zone of avoidance is there because of the existence of, because the Milky Way itself, the dust and gas of the Milky Way blocks that view. So there is a huge gap that it can't be seen and never shall be seen because of the Milky Way blocking it. But on this size scale, when we're looking at velocity space of up to 5,000 kilometers per second of recession velocity, that gets us out to some rather large galaxy clusters such as Coma and Abell 1367. But you see that Virgo cluster is about 65 million light years away, so that we would go 5 times that distance. So we go out to about 300 million light years away to get us to the Coma cluster, as well as Abell 1367. We take and we rotate the view because that was an X and Y view. Now we look at it from above, from the z-axis looking down, and we see the zone of avoidance from there, and we see the Virgo cluster off to the side, and we can see slightly different versions of the filamentary and group-like structure of the local universe. And we can rotate it again to see the pancakey sort of structure of the entire environment. So it is kind of flat, actually. There's a very pancakey structure to the entire local universe. So now we can kind of group it and see how things look in sort of a density sort of format. So we have red where it's most dense and blue where it's least dense and nothing where it isn't dense. And we see there's big groups by the Hercules cluster. The Great Wall is intruding in. It's just poking into the view. And from a different angle, we see the Great Wall poking through again. And this is where it gets interesting and how we begin to start to define the nature of Laniakea. So notice all these little dots, and this is what Courtois, Helene et al. Did in order to try to begin the mapping. And this is a major achievement of actually being able to take the actual velocity data out of the flow and show you how things move in the sky because of the local flow that they must have. So we zoom back and forth between the two images and go back and forth between the velocity space and others. And we find that we're in part of a large group that's falling towards the Great Attractor. So the Virgo cluster, in which we are in the kind of center right, is flowing towards this red area. And the blue is where things are flowing out of. The red is where things are flowing into, and the blue is flowing out. So these things are traveling on the order of thousands of kilometers per second, and we're looking at things that are millions upon millions of light years in size. So the Great Attractor is not visible due to the zone of avoidance because the Milky Way is blocking it, so we can't see it. But we can measure the flow or the apparent flow by seeing the residual speed away from the Hubble diagram, away from the Hubble flow. And so then we can look at a slightly different view that shows us the Virgo cluster flowing towards the Great Attractor and leaving behind an enormous, enormous void. The blue is where the voids are, the Great Attractors are the red are. And this shows how things apparently are flowing in the local rivers of the universe. And again, here's another amazing view of it that shows how the flow is going towards there's the local void, and how everything's kind of flowing towards both the Fornax cluster, the Virgo cluster, and then that's all going towards the Great Attractor. And so what we have is, that's the flow diagram, and then if we take that flow diagram and say, really what's actually grouped together, we can name those groups, and we find that there are all these superclusters in and around our area. And we find that the superclusters are the local billion light years in area. The Laniakea group supercluster is in yellow in here, but we see all these other superclusters that are around us. And superclusters make up the largest size scale objects in the cosmos and are composed of enormous numbers of galaxies with vast distances between them. And the Laniakea group is not necessarily a gravitationally bound group. Most of these large stringy superclusters are not, but the clusters within them are. So there's a bit about our local cosmos just within the nearest billion light years and how we found it using redshift surveys and groups and clusters. And we'll see you next time.